All right, we're going to move on to chapter 21C, where we talk a little bit more about rates of change. A lot of what we're going to talk about here we've kind of touched on before. It's just we're actually going to have a little bit of time to practice it. So, just as a reminder, we're dealing with rates of change here. We can think about that as slope. We can think gradient. We can think when we find the derivative is a function that lets us find our slopes and our rates of change and our gradients and all these things. And so we're going to be working through some word problems in 21C that you might actually use a derivative function for to help you with. We're going to look at how to do the mathematical way, the derivative function, but then also look at, well, what can we do graphically to help us out? How can we be efficient with what we're doing? So let's get started. So this says if s of t, so we have a function s of t, gives the distance traveled by a runner, s prime of t, so this means our derivative function. So if this is our standard function, s of t, that means it's t is our variable within this function. So it could be something like 2t plus 1, something like that. It could be quadratic, 2t squared. But it's t is our variable, gives the distance traveled by a runner. Then what does the derivative give us? Well, our derivative function, remember, is also your gradient function, and it is your change in y over your change in x. So whenever we find our slope, we would be looking at our difference in our y's over our difference in our x's, but it's y's over x's. So distance traveled by a runner over given a certain amount of time. So it's change in distance over change in time, which you can think of as speed. How much distance do you change over a certain amount of time? You can think about that as the speed of the runner. So if you know how far the runner's made it after a certain amount of time, your derivative function is going to be your change in distance over time, which is going to be your speed. You could think miles per hour. You could think meters per second. But distance over time is our speed. For the second one, it says h of t gives the height of a tree over time. So what's the derivative give? Well, it's over time. T is our variable, time. So this is going to be change in height over change in time. So you can think about this as how much is it growing per year, rate of growth. So this could be rate of growth, change in height over our change in time, change in height over time. If t gives the temperature after m minutes on a certain day, what does dF over dm give? This should be dt. I don't know why it's dF, so that should be dt. So this is, remember with our dt over dm, this is our difference in t's over our difference in minutes. So it's our change in t, so it's the change in temperature, which is our y value, change in temperature, over change in minutes, or time. So it's how fast is the temperature increasing or decreasing. So whenever we find our derivative function, it's good to, when we have a word problem, take a note of like what would our derivative even mean, and that's what I was working with there. So for question 1, the volume of a hot air balloon after t minutes is given by this equation. So we are putting air into a hot air balloon, or taking it out, I'm not sure, we'll need to look at it. But the volume of air inside the balloon is given by this. So V is the volume over a certain amount of time. Our time is in minutes. Find the initial volume of the air in the balloon. We want to know how much air is in the balloon, initial, is when t equals 0. We don't want to know how fast the volume is changing. We just want to know how much volume there is. So to do this, we just do a direct substitution. We plug 0 into our original function. And 0, 0, 0, 2. So to what's the volume in a hot air balloon? Our volume is 2. It doesn't give us any units for the volume, so it's just 2 is our initial volume. Find the volume of air in the balloon after, when t is 8, so at 8 minutes. Now once again, this doesn't say what's the change in volume, how fast is the volume increasing when t is 8. It just says what is the volume, find the volume. So we're just going to plug 8 in directly. And I'll use my calculator here. Okay, it seems like my last video broke. So we got it fixed now, I think. So I'll have to do a little video editing, put these together. But what I was doing whenever it malfunctioned is we were plugging in 8 directly into our function, because this function gives us the volume of a balloon after a certain amount of time. We are looking at find the volume at when t is 8. So we plugged in 8. So from here, it seems like the volume of our balloon is increasing because we had an initial volume when time is 0 of 2, and now after 8 minutes, our volume is at 914. Part C says find the average rate of change, okay? Average rate of change. Notice this does not say instantaneous rate of change. It doesn't say gradient. It just says average rate of change. So this is going back to our very first or second section of chapter 20, where we used our slope formula. In order to find our average rate of change. So first 4 minutes. So what we need is when time is 0, the volume of our balloon is 2. And after 4 minutes, what's the volume of our balloon? We need our 2 points so we can use our slope formula to find our average rate of change. I can keep plugging in, so if I want to, I can go back, I can change my 8 to a 4. Anytime you can learn the quick calculator techniques, it's going to be good for you, speed you up on your exam. And we get 122. I can also type my function directly into my y equals and get all my values from the table. So x cubed, 2x cubed minus 3x squared plus 10x plus 2. It's probably going to go off, yeah, it goes off my graph, that's all right. Generates a table, and we could pull them from here. So if you want to save yourself a little time, there's our initial volume of 2. It looks like it's increasing. 5, 6. There was our 8 of 914, and at 4 we have 122. So however you want to find your points. We find both of our points, and then we plug them into our slope formula. So y2 is 122 minus y1 is 2 over 4 minus 0. So 120 over 4 gives us 30. So 30 is our average change in volume for the first 4 minutes. Okay. Part D says find the rate of increase in volume when t equals 4. Now this wants the rate of increase in volume. It does not say just what's the volume, it says what's the rate of increase of volume when t equals 4. Well, when time is 4 from my table, it does look like it's going up. Because at 3 it's 59, 4 it's 122, 5 it's 227. So at 4 it is increasing, so I should expect to have a positive rate of change. So we can go, you could, algebraically, find the derivative, figure out what the derivative is at 4, and that would be your answer. Calculator-wise, we can go second, calculate. Number 6 will give us our rate of change or our slope or our gradient, however you want to think about it. It's our rate of increase, our rate of change at plus 4, enter, and we should have a rate of increase of 82. So I know that you guys like to write your calculator steps, so if you want to use the calculator method, y equals type in the function, second, calculate number 6, type 4, enter, and it says dy over dx is 82. That's the calculator method. I just want to show you how the algebraic method is going to get you the same point, because you are going to need to be able to do the algebraic method occasionally on the IB exam, and I don't want you to be without that skill. So that's the calculator method where we can get to the correct answer. Algebraically, I'm going to start with my original function. I'm going to find the derivative, which allows me to find rates of change or slope. So dv over dt. It's usually dy, v is the y though, over dx, but t is our x. So it's dv over dt. We drop our powers. So the 3 drops, 6t squared. 2 drops here, minus 6t, 2 becomes a 1, plus 10, and remember we ignore our constants. So here we are. I want to figure out the rate of increase when t is 4. So I'm going to plug t equals 4 into there. So we do 6 times 4 squared minus 6 times 4 plus 10, 82. The reason I want you to be able to do that is the IB exam might ask you, show this step. They might want you to find the derivative. Then they might want to show 4 plugged in. So I want you to be able to show this work. Notice you get the same thing. This is our rate of increase at that moment. This is the instantaneous rate of increase in volume when t is 4. It's increasing by 82, whatever volume is in, cubic inches per minute, something like that. All right, on the back, this is another example of a place where you might use this with cost. So the first thing it says the cost of producing X items in a factory each day is given by this. So C of X, the cost of producing X items. This one says C prime of X means this, remember this is the derivative, wants us to find the derivative. So we are set up where we can just find the derivative right away here. So our C prime of X, our derivative function, drop your exponents. So we have to take that decimal times 2. 0.00013 times 2. So we can handle scientific notation. Or, let's see, how does this go? Decimal? Nope, doesn't work. Okay, so that would be 0.00026 x. Then we take this times 2, so 0.002 times 2. Oops, that's a typo. This should be a 3. We shouldn't have 2 2's. So let me go back. That's a typo. 0.000123 times 3. So this is the same thing, but that should be 39 x squared. Now we do 0.002 times 2. So plus 0.004 x, because the 2 drops down to a 1 exponent, plus 5, and we ignore our constant. So this is our derivative function. So find the change in cost over items. So it tells us the change in cost for each item produced. So find C prime of 150 and explain what this means. So we want to take 150 and plug it in there. Since it says C prime, it wants us to plug it into this derivative function. So there's our derivative function. We can plug it straight in here. I'm going to show you the algebraic way too, just so you have lots of strategies. So for once we get to 150 items produced, this is our rate of increase. So this is our rate of change. So once you get to 150 items, for every item you produce more, each item, it's an additional $14 more to produce the item, $14.37. Okay? So that's our rate of change, cost per item. So once you get to 150, the increase in cost per item to produce is $14. Typically, when you're kind of like down lower, each item's going to cost more and more to produce, but if you produce a ton of items, if you produce a lot of items, then it might be less for each item, okay, because you're able to buy in bulk. You'll be able to buy your supplies in greater bulk at a time and that type of thing, which would then slow down your rate of change, okay. Additionally, at some point, it might get a little more expensive because you have to start paying your workers overtime, and so that might make it go up. So these are variances that change how much it would cost to produce items. So not more, really. At 150 items, each item costs $14.38 to produce. So if you wanted to go up one more item, it costs that much more. Graphically, the way we can figure this out is if we graph our original function, this one all the way up here, 0.00013x, I changed it to cubed, plus 0.002x squared, plus 5x, plus 200. This is our derivative evaluated at 150 for part B. So we can go second, calculate number 6 at 150. Oops, didn't like that. Bet it wants me to zoom out. So let's see, 150, let's make it 160. Our Y value maybe 5,000. Just do a little changing around here. Let's see how that works. It just didn't like it because it was so far off of my graph. So there it is. Over time, it looks like it's actually getting a little more expensive to produce each item. So maybe that has to do with labor or something. So we're going to calculate the derivative at 150. There we go. Same thing, 14.375. For part C, it says find out the cost at 151 minus 150. At 151, now here's a strategy you can use in your table because this is a little bit annoying. I want to find my original function, this original function with this plugged in, so I can use my table for that. You can go to your window, second window, and you can change this table start value. So some of you guys might have figured this out, but we could have our table start at 150. That way we don't have to scroll so long. So the cost at 151 is $3,448.20 minus the cost at 150 is $3,433.8. So we're looking at to produce 150 items, this is how much it cost. To produce 151 items, this is how much it cost. So the difference is going to tell us how much did it cost to produce that one item. So if we produce 150, we paid this much money. If we produce 151, we paid this much money. So the difference is the increase from here to here, which is going to be how much it costs to produce that single item. So let's subtract those. 3,448.2 minus 3,433.8. $14.4. Notice how close that is to this. Okay, 14.4. So this is how much it costs to produce that single item. The 151st item cost this much to produce. This was saying at 150 items, that's the increase. That's how much it's costing per item as you go on. Okay, so those items should be similar. Your homework is posted on Canvas, so please go there, take a look at it, and make sure you are working hard. Thanks for watching.